Good afternoon, everyone, and welcome to today's webinar. It's 1 o'clock now, so we're going to go and get started here. My name is Elliot Nauer. I'm an outreach specialist with the Southern Fire Exchange based out at North Carolina State University. And I'm joined today by David Godwin, the director of the Southern Fire Exchange out of University of Florida, and Marynell Armstrong, an outreach specialist based out of Tall Timbers Research Station. Today, we're going to be hearing from Kate Jones, a PhD candidate at North Carolina State University. And she'll be talking about her work on FireHydro, which is a fire risk mapping project focused on South Florida. And now, without further ado, I'm glad to introduce my good friend here at NC State, Kate Jones. Kate is a PhD candidate in the Center for Geospatial Analytics within the College of Natural Resources here at NC State. She works on a variety of wildland fire-related projects, including geospatial analyses of national-scale wildfire management data, also forecasts of future land management and prescribed fire smoke scenarios, and data visualizations for long-term fire ecology monitoring, as well as strategies for effective fire science communications. So Kate received her BA in Geospatial and Environmental Analysis from Virginia Tech and a master's in geography from Oregon State University. Her master's work at the H.J. Andrews Experimental Forest combined forest ecology and spatial statistics and solidified her interest in co-producing management-relevant science. Prior to beginning her PhD here at NC State, she worked as a researcher at the National Energy Technology Lab in Albany, Oregon, where she helped create decision support tools for environmental assessments. And without further ado, I'll turn it over to Kate to introduce herself and tell us about the FireHydro project.
Well, thanks, Elliot, for the introduction. Thank you all for joining today. As Elliot said, my name is Kate Jones, and I am a PhD candidate in the Center for Geospatial Analytics at NC State. And I have been working with my advisor, Dr. Jelena Vukmanovic, and a slew of people with the National Park Service and otherwise in South Florida, so specifically Big Cypress National Preserve and Everglades National Park, to develop a model we call FireHydro. And really, the name FireHydro pays tribute to the fact that fire behavior, fire spread is so clearly linked to hydrology and water levels in this landscape. So this project wouldn't exist without the number of managers and fire management staff, again, in the National Park Service who have given their time and insight. And I will claim I am no expert in this subject matter. I'm just the geospatial support. So I do also want to quickly thank Troy Hill and Krishna Singh, which are two individuals that worked on an earlier version of FireHydro and really laid the groundwork for this project. So FireHydro, essentially we are trying to map fire risk using field types or vegetation and water levels. So how deep and where is water occurring across this relatively flat landscape? And so ultimately the purpose of FireHydro is to help fire managers more efficiently and effectively suppress wildfires. So using natural landscape features, wetted fire breaks, by having a more fine scale spatial understanding of where water and fuels are on the landscape. And then also to successfully conduct prescribed burns. So giving them some mapping products ahead of time before they go out and do some field-based assessments. So let me turn on my highlighted pointer here. So as I'm gesturing around, I'm actually pointing at things on the screen. So the roadmap today, I will start off by setting the stage for why South Florida is an interesting place to think about wildland fire management and place-based geospatial decision support tools. I see many people in the chat are from Florida, so I probably don't have to make too much of a case there. I'll then move into kind of the unique data components of our model, how we started thinking about this project, the evolution of the model itself. I'll then share some of our working model outputs, share a couple of issues that we're still troubleshooting. So this is truly a work in progress, going back and forth with fire managers and iterating here and there, where we'd like this to go in the future. And then depending on how we are on time, I will share maybe a couple slides of just how managers will interact with and run the model on their local machines. Oh. There we go. All right. So why South Florida? I've adapted this term ecosystem fire from John Keeley, really to bring in kind of 4 components that are critical for thinking about fire in this landscape. So on the left here, we have seasonality, and that means seasonality of precipitation as well as temperature. So in this top left plot, we have months of the year across the x-axis, mean precipitation in centimeters, so average monthly rainfall, and then mean temperature on the right y-axis. And as you can see, there's a peak and kind of a decline in both of those, so seasonality throughout the year, but really we're heavily driven by these drier winters. So we get lots of precipitation in June to September, starts to decline, dry out through the winter months. And yes, we do have, temperatures getting warmer into the summer months, but as we know, it's relatively hot in South Florida. So driven by temperature or precipitation, amplified a little bit by temperature when we're thinking about fire season, wildfire season, specifically in April and May, and really prime prescribed fire season in January and March. So we can also think about productivity of the fuel. So this series or time series of images here is taken in the Florida Panther National Wildlife Refuge that's just west of Big Cypress. So we have an image of pre-burn, immediately post-burn, all the way out to 2 years. And so getting a snapshot of how those fuels are regenerating and then coming back up to somewhat near pre-burn fuel loads relatively quickly after a burn. So growth here in vegetation is neither temperature nor moisture limited in most cases. On the bottom right, we can think about fuel structure and less so talking about canopy, understory, all the way up to overstory, but more about the variety of fuels that occur on this landscape and their spatial arrangement. So this 4-panel image here just shows 4 of the 11 fuel types that we use in our FireHydro model, but you can see a low load, fairly sparse dry grass to coarser, higher fuel load, wetter grasses into their pine, and understory shrub and grass communities, and then these unique environments that are tree hammocks. So kind of these little islands, if you will, or tree islands across the landscape surrounded by oftentimes wetter environments. And so if we think about how these 4 and the other 7 field types occur across this landscape, we have the map in the bottom right that shows Miami and incredibly heavily developed urban, suburban development to the east. As we wrap around into the north, you can see some very intense agriculture, and then to the northwest, slightly less dense development and still some agriculture. But really our area of interest is this mostly natural looking, undeveloped area of South Florida. So Big Cypress Reserve, roughly in this area, Everglades National Park here, and then the water conservation areas, which I'll show a more detailed map with boundaries. But really the take home here is as you look at this satellite image, you can see these fine scale changes and different colors and the representation of how water is retained on the landscape and the fuels that grow there. And so finally, we are not ignition limited in this landscape. I think sometimes Florida is referred to as the lightning capital of the United States. There are a number of lightning ignitions happening here. There are also plenty of access roads, campgrounds for human accidental ignited wildfires, and then most unique and incredibly healthy prescribed burn program. So Everglades National Park, I believe, was the first official national park to conduct a prescribed burn back in the mid-1900s. And they're still burning on the order of thousands of acres in single burns or over a couple of burn units. So a lot of fire happening here. So where we have lots of fire, we're looking to manage fire, specifically conduct prescribed burns, implementing these decision support tools are really drawing on the spatial data that's available for this area. So the map on the left shows fire footprints or burn boundaries that are all overlaid over one another from, I believe it's 1980 all the way up to 2018. So in the blue, we have prescribed fires, red are human ignited wildfires, and yellow are lightning ignited wildfires. And while you can't see every single fire footprint that's happening here, the take home point is there is a significant amount of fire over a large spatial extent occurring in both of these parks. But we're not just interested in fire in space and what are the spatial boundaries, but again, that timing component, thinking about seasonality. So I have highlighted here this pink box, which again, we have months of the year across the top of this plot, and now we're descending through time. So from 1980 into the present, or 2018, so several years back. But within this pink box, we're interested in this transition or being able to model and map this transition from mostly blue dominated dots into seeing more red, and then into May and June, certainly larger wildfires coming online in the yellow and red. And so the size of the dot here is scaled to the fire size, the colors corresponding to the map legend on the left. And as we move in January, February, and March into April and May, we go from months where prescribed fire conditions are generally quite good directly into wildfire season. And so much of this is dependent on the drying of the landscape, or how those water levels are receding at any given time in any given place. So the fire footprints and fire temporal patterns, hydrology, are not happening in a vacuum in this landscape. So there is a significant urban, suburban, agriculture footprint here. This map in the top left shows developed, protected, and other. So the red being what was considered urban in 2010. So this is a little bit dated. The other areas, so not designated as protected, again, is a combination of less dense development, some open area, agriculture, and ultimately how this development, more people moving in, needs to really alter and change where water is flowing, prevent flooding, have led us to somewhat of a pattern of changing what we would consider the natural or pre-settlement flow in this area. So the graphic on the bottom left shows, again, a very generalized map of what natural flow might look, mostly north to south, and then spreading out along the coast. Current flow, again, an abstraction, but really heavily more east-west directional. We've lost a lot of that overland flow and subsurface from Lake Okeechobee down into the parks. And then we have what could be a single restored flow plan. So one iteration of the future through ecological restoration, and specifically through water control infrastructure. So across this landscape, there are canals, berms, roads, pumps. It's a heavily managed system, really, of water flow into different areas, even within this protected and natural landscape. So again, within this natural landscape, we have a mosaic of fuels. We have a presence of water at different depths and different spatial patterns throughout the year, and that can change over really fine spatial scales. So the map on the left shows an example of a grass fuel type that certainly has available fuels to burn, but directly adjacent to it. So on the order of a couple of meters, we're seeing standing water within this fuel type. And we're not able to model it 1 meter or 2 meters, but if you take this idea of fuels directly adjacent to standing water and scale that up, this is happening at also larger spatial scales. And so the idea that at some point we might have enough water on the landscape or in certain fuel types to prohibit fire from traveling, and vice versa, have it recede to exceptionally low levels that lead to unexpected or relatively high fire danger. And so this is a small scale example in this photo, but what we really want to mimic and kind of understand is this transition from open water, very coastal vegetation. Over the course of tens of kilometers, we move inland to cypress and pinelands that are not always occurring in slightly more upland topography, but relatively so to some of the more low-lying areas. And so keeping in mind that we have this transition even over really small amounts of elevation in vegetation communities and variety that we see across this landscape. And then the image in the bottom right shows just how much a single piece of infrastructure or this barrier that changes how water might flow across this landscape. We have heavy fuel loading trees, denser canopy to the left side of the road compared to less fuels and open water on the right side. So these transitions of how much water and what type of fuel can again occur over really fine spatial scales. And finally, setting the stage for West South Florida, we have 4 different maps here of different fire danger or fire risk indices. And these are all taken for the same date, so April 6th of 2023. And they're all drawing on different data, so we don't expect them to be identical or aligned perfectly. We do have some, if you look at the deep greens or kind of lime greens, that's low or moderately low risk, some yellows in this image here, yellow and green. But then we have this anomaly of very high, severe fire danger on the same day. And so two things, there's uncertainty introduced when you have such a variety of possible risk prediction. And then two, none of these national level indices or more drought related indices are really capturing local hydrologic behavior and water levels. And so that sets the stage for why we need to be thinking about other more local important variables in this place-based fire risk tool. So now that led us to developing FireHydro. FireHydro in its essence is, it can be run daily. It's a geospatial decision support tool. Now, it's not to say that the outputs are always relevant on a day-to-day basis. Water levels are not changing generally dramatically overnight. They have the ability to run it daily, but weekly or bi-weekly might be more appropriate. And it is trying to characterize fire risk. And so when I say fire risk, I know there's a lot of precision definitions of risk out there. We're simply trying to look at how fire might move across this landscape based on the fuels and the water levels on that given day. And so we are concerned with water levels and fuel type. So those are the two main core components of data that go into this model for creating the if-then statements, which I'll explain on the next couple of slides. But we do use some other data components to really round out the model. And so this is an example on the right of an output of FireHydro. It is right now a 5-class risk map from high to low. And these are kind of 3 sub areas within the model. So managers can select which of these areas they run at a given time, but both of our national parks and then the water conservation areas, which are managed for the most part by the South Florida Water Management District. So we started with FireHydro version 1, and let's go with the cursor. Lost my little red dot. So FireHydro version 1 is an output here is on the left in this map. You can see in the grayed out or black areas, we don't have data coverage there. So we're missing part of a DEM, part fuels information. And so we knew we had some basic data input improvements to make. But we also were originally trying to assign risk in a more universal way. So if we look, and by universal, I mean anywhere on the landscape, if the fuel type was cypress and the water level was a foot above surface, then your fire risk was high, medium, high, moderate, moderately low, low. But if you look at this graphic again on the bottom, I think I have this several places throughout this presentation, helps center me on what we're talking about. This is not a universal or uniform landscape. And certainly these fuels are not experiencing the same amount of water for the same durations, regardless of even if it's the same fuel type, potentially where it is on the landscape makes a difference. And certainly from the right side of this diagram to the left side of this diagram. So in making some of those sort of simplified universal rules, we ran into some issues. So this is an output from FireHydro version 1, and this was run, I believe, several days after Hurricane Irma. So Irma came through, I believe, somewhere on August 30th, 2017. This is a run for early September, and ultimately we end up with areas that are still showing high risk, moderately high. We have a whole rainbow of colors here going on, when in reality, talking with fire managers in this landscape, this whole map should be low risk. It should be dark green through and through. And so this is where we really started to have conversations about how can we take a data-driven approach, but absolutely bring in management expertise and people who are walking around this landscape all the time, do a data-driven approach, but have them be able to inform and modify these risk relationships with their local knowledge. So I will step through, I'll give you an overview of more or less the 6 data products that we use now, some of which are new in version 2, some of which have been updated from version 1. And the 4 here on the top are kind of the main players, and I'll spend a little time later on talking about energy release component and fire history. But we changed, or we updated, the digital elevation model, also known as a DEM, which simply allows us to have elevation and an understanding of topography across this entire landscape. We then continued using USGS-based water surface, which I'll share about in more detail. So these water levels, same input data product or raw data product going in, but we've adjusted how we incorporate them into the model and the risk assignment. And then on the right here, we have management areas, which is new to FireHydro version 2. Really brings in some of that kind of more localized finding, like fuels, like water levels across this landscape. And then finally, we were able to bring in some updated, so higher spatial resolution and higher resolution in the fuel type or vegetation community classifications, thanks to some work done by other folks in South Florida. And we'll circle back around to ERC, energy release component, fire history in a little bit. So to give a visual of what it means to improve the resolution of a digital elevation model or DEM, you can look in the panel here on the left, highlighted in red. You're able to pick out features of the landscape, the actual ground surface. But as we move over to the right and what's highlighted in green, in higher resolution, you're just simply able to see more detail about what's happening on the landscape, how the ground surface is changing, slopes, et cetera. And so in this incredibly flat landscape, having a higher resolution DEM is important because we see small changes in elevation happening at really fine spatial scales. And when you use a coarser resolution DEM, you lose some of that detail. And so this white square over here on the right shows the original resolution of the DEM at 400 meters, so somewhere 4 football fields, give or take. And we were able to create a DEM using separate data products that are more or less newly available at this 5 meter or the size of this pink square here. And the model can be run at a variety of resolutions in between. So anytime you have just 2 of something, it's hard to know what's right or appropriate. So there was the original DEM for FireHydro in version 1 is shown on the left here. And then our updated DEM that we're using essentially in FireHydro version 2 is on the right. And because we just have 2 DEMs, each one of them have their own biases. So they're biased high in some places, biased low in some places. There are different spatial resolutions, but we're still waiting for a third DEM to be produced for this area so we can kind of do a little more calibration and validation because ultimately our DEM, as I'll explain, affects our water risk outputs. So we are able to capture more detail in the DEM on the right. So in these pink boxes, I've just highlighted areas where, in this pink box, it's not represented in the DEM on the left, but we're able to pick out buildings. And actually in some cases, I think these are landfills that really stand out above ground surface. But we're also able to get a bit more better resolution in transitions or natural boundaries, roads within our area of interest. So our second data piece are the water surfaces, and these are from the Everglades Depth Estimation Network. Acronym is EDEN, and this is maintained by the USGS, United States Geological Survey. The map on the left shows, I believe it's approximately, at any given time, 200 gauges that are online here. So actively collecting water level measurements, water depths. And these gauge or point-based locations are then used, are interpolated or modeled to create this smooth water surface. So in places where it's deeper blue, water is deeper, more water, lighter colors, less water. So these are produced on a daily basis. And one of the, truly kind of the linchpin of all these data products are these water surfaces, because the USGS has maintained this gauge network. It makes it sort of a living laboratory to have this long-term data and be able to rely on it for future model use. So we can't just use the DEM and the water surface in isolation. What we really want is a water level for our model. So we subtract the digital elevation model from the water surface produced from EDEN, and we end up, this is an example map of water level. So this is produced in centimeters, but for the purpose of display, where we have deeper blues, you see deeper water levels on this day, and where we're in light white, shallower water levels. And it is critical to note here that deeper and shallower are kind of relative. as water is deep, that water is above the ground surface. So you might see standing water a lot or a little. But as those water level values become negative, water can recede beneath the ground surface. So it doesn't mean that the landscape is immediately dry at that point. You can still have wetted areas as the water level measurements recede. But as you get too low, then you have significant drying in a number of places. So our third data product, I guess it is, are our field types. So you'll see in the legend on the left, I realize it's sort of a jumble of letters and numbers here, but all these fuel types do map to the National Fire Danger Rating System fuel models. And these were, in theory, kind of custom. Yes, they exist at a national scale, but the vegetation and ecological communities that were mapped to these individual fuel models was mostly custom done for this landscape. So you'll see in Big Cypress, which is mostly characterized by the lime green and the royal blue here, and into Everglades, we have really fine resolution. You can see, the shapes of some of the strands and behavior in the sloughs just from the vegetation data. And then we also have coverage in the water conservation areas. Oh, and I should say that this higher resolution data was developed by Pablo Ruiz and others. And I do think they're working on extending this vegetation coverage. But for now, we've had to kind of merge in another vegetation or fuels data set in the water conservation areas that doesn't quite have the same level of detail. So you'll see we have, gray and Everglades that really just continues and begins to dominate into the water conservation areas, which not to say that there isn't a large presence of GR8 here, but we haven't gone through that fine scale crosswalk of different vegetation to field types. And finally, our management areas. There we go. Our goal in incorporating the management areas these are kind of very broad strokes boundaries, thinking about similar fire management strategies, objectives, and eventually getting to similar water levels. So if you had the same field type within this management area, it might be more likely to experience same water depth, similar water depths for a certain or similar duration throughout the year than, say, the same field type in another management area. Now, this system is not perfect, but it gets us a little closer to not just making those universal, if field type is this, then water level is this statements. So now that we have, we've done a little bit of processing on our water surface using our DEM, we want to combine our water levels, our fuels data, and the management areas to get to kind of the nuts and bolts of how our if-then statements work in this model. So we have over here on the left, again, that same water level map. In pink, this is not quite to scale, but I've tried to highlight what would be, a single pixel or a single grid cell in this water level map. For each grid cell, we gathered, again, thanks to the existing and archived Eden data, we gathered from January 1st, 2017 to January 1st, 2023, 312 regularly sampled days of water level. So one per week across this 5 or 6 year period. And once we have those water levels for every single cell, we can start to sort the water levels by which ones are highest, which ones are lowest. And we end up with kind of a percentile ranking here. So the water levels that are the highest, you can think about as being shown in green. As you move to somewhere in the middle, you see a little less risk. So again, these colors corresponding to how we might think about risk. And then finally, once you get to the 97th percentile of the driest or lowest water levels, you would certainly think you'd have different fire risk within that pixel. And so we take this ordering of water levels and we simply create a distribution. So this is a real data-driven piece that is not correct on its own. It certainly needs modification, but it creates a starting place for thinking about how these water levels change across the landscape and also maybe through time. So this distribution shows water level on the x-axis. So anywhere where you're above 0, you would expect to have essentially water above the surface. Anywhere where you're below 0, you expect to have water at or beneath the surface. And essentially through some issues with our DEM, and again, doing some fine tuning across those two DEMs we have from version 1 and version 2, the actual values of these positive and negative numbers are certainly open to change and calibration, but the idea of thinking about we spend, instead of focusing on maybe the exact centimeters above and below the surface, thinking about how much time are we spending in the driest part of our distribution, moderately high risk, moderately low risk. And so essentially here we're saying 40% of our data, we've broken it down by these percentile thresholds. 40% of the data we'll categorize as we're in low fire risk. And so this kind of percentile break strategy is a takeoff of how a number of different fire management indices and risk breaks occur, thinking about the 97th, the 90th, the 80th percentile to delineate risk. We've just modified those percentiles a little bit here. So we don't just want to think about water levels on a per pixel basis. So this is an example of the low load humid climate shrub, or what's pine and dominated by grass and shrubs underneath. And this is for every SH6 area on the landscape, the distribution of water levels. So again, that 90th, 80th, 60th, 70th, 60th, 50th percentile, thinking about these fuels. And so that's great in isolation. We can create these distributions for individual fuel types, but really we want to know how these fuel types differ from one another. So if you squint and you kind of zoom back, you might say, these all kind of look quite similar to one another. And so here I've replaced the names of, TL4, SH6 with photos and some more descriptive naming here. But the plot is still the same. So we have water level in centimeters across the x-axis and density along the y-axis. So that's simply how frequently are we seeing a water level of 0 centimeters within our urban vegetation classification. And I mean, these photos are certainly not characteristic of exactly what that fuel type or fuel model is on the landscape, but these are kind of through the vegetation classification that was worked on with the fire managers. These classifications are representative of the fuel models across the landscape. And so these are just photos we use to kind of jog our memories. But some differences across these different densities, in moderate load humid climate shrub, we see a very peaky distribution with less tail, very, very high water levels, or less tail and very, very low water levels, compared to low load humid climate shrub. Looks different, slightly different than the agriculture distribution, with fairly long tails or days of high water days, days of low water days. And so this was a useful exercise to understand, if at all, how the water history, so thinking about those historical water levels, how they may be different across different fuel types. But really, what we want to know is how those distributions and risk thresholds could differ across different field types and across different management areas. So in this case, I've just taken 2 field types. So instead of looking at all 11, but we're now looking at low load humid climate shrub and low load broadleaf litter in a side-by-side plot comparison of North 75. So this purple area here above Interstate 75 in Big Cypress, South 41 is here in gray, and then in blue, we have the Pinelands and Everglades. And so we're not so much interested in this case comparing between or across fuel types, but going back to this idea that different fuel types in different locations across the landscape will experience different water levels for different durations throughout the year. And so in North 75, looking at low load humid climate shrub, we have this longer tail with kind of this bump in density of low risk days. And we're centered a little bit on the left side, so on the low side of 0 here. Whereas if you look for the same fuel type, also SH6, in South 41, we have more days occurring right on that 0 cusp. We lose our long tails over here. And similar distribution shape, maybe, to North 75 we have in the Pinelands, but we don't have that really positive tail of very wet days like we do see in North 75. And you can see some of the same patterns unique to the different low load broadleaf litter distributions. But this really jogged our brains, got us talking about, okay, we are seeing, even if slightly different water level distributions with different risk thresholding that are occurring at different water levels in our different fuel types. So we made some maps based on those initial risk thresholds or risk breaks, knowing that they would inevitably be wrong, hopefully more correct in some places, more wrong in other places. But we had the benefit or the pleasure to go to South Florida and actually meet with the folks there in Everglades National Park and Big Cypress that we've been really meeting with over Zoom for years at that point, thanks to the pandemic. And so we took some paper maps with us, and for April 9th of 2023, we printed out a map of what we essentially estimated fire risk would be. And I'm very clear to not use the word predict there. We don't have any predictive power. There are no uncertainty bounds on these classifications. It's really more of a perceived relative risk across the landscape. And so we sat down with them and we got to drawing on the map and essentially highlighting areas where we were significantly or even just a little bit over predicting risk or under predicting risk. And if you can see, I think, some of we use like a marker red dry erase marker to do this, and some pencil and pens. But the blue squares here highlight where we adjusted management area boundaries. So getting back to the idea of a management area, this maybe differed in its utility here by not just grouping like fire management, really starting to say, where do we have like hydrology or similar conditions within a given management area? And so we did some lumping and some splitting, some conversation about, well, why this area, why not this area? And that really gave us a better idea of where our risk predictions were most off. And so the take-home point from this slide is this will continue to evolve. We've adjusted our management areas. We've played around with different risk threshold breaks, so that 90th, 80th, 70th percentile. But essentially, the real improvement in this model and the utility moving forward is their ability to go out and field validate, to prioritize certain management areas and certain field types, and for us to design this model in a way that will evolve into the future. So they do have, ownership and ability to edit these risk outputs with their expert knowledge. And so this is just a depiction of the kind of the output of our lumping and splitting management areas. We went from 14 on the left here, original management areas, to 17 on the right, and those differences are highlighted in white here. So for recap and kind of diagram and workflow of how all these pieces come together, we start off with a daily Eden water surface, so produced by the USGS. We then subtract from that the DEM that we created, and we're only using the DEM within our area of interest. We don't need that larger extent that we actually produced, and that gives us a water level for every location on the landscape. We then make sure each water level, so each pixel, has assigned a fuel type as well as a management area. And so we end up with, like I said, we had 17 management areas. We have 11 fuel types. I think it's 180 some odd risk curves. Now, not every fuel type occurs in every management area, but we're able to essentially automate the production of these risk curves and looking at historical water levels, with the idea that if I get to it at the end, if I have time, showing you that managers are able to customize these relationships through an input CSV. So they're, again, data-driven, but definitely intended to be modified to get to a more accurate 5-class risk map output. And so for those that don't want to see a workflow diagram, these are the actual simplified if and then statements that we use within the model. And I have mostly here grayed out, again, burn history and energy release component. I'll step through those in just a minute, but these are the 3 main considerations that then come into the 5-class fire risk map and the output. So after all of that, we'll actually look at some outputs and talk about some of the pros and cons and things that we know we can do to improve the model into the future. This is an output of FireHydro, and it can be run daily. Again, that's not necessarily the temporal resolution that they need, but they have that option because of the available water surfaces. It's output at approximately a 30-meter resolution, and every bit of the design of this map has been informed by by fire managers. That doesn't mean that we're doing a perfect job yet, but these products wouldn't be possible without their input. So to think about a couple of sort of characteristic days that we might see in South Florida, we've run a wildfire, so the Jarhead in 2011. In the center, we have a good prescribed fire day, or a day where management outcomes were met. And this is for April of 2019. And then we have finally achieved our very green risk map post Irma. So a couple things to point out on the left here, you can see the boundary, hopefully in black, of the Jarhead fire. I know that there is a whole lot more that goes into fire spread and the final footprint of a fire than just the mapped field types and the water levels, wind speeds, et cetera. We are not capturing any of those things, but it is somewhat encouraging that we see the fire burning in high and moderately high risk areas, and sort of this contour along the northeastern and eastern boundary where it aligns with where we say risk was reduced, maybe due to more water being on the landscape. This can both assist manually input fuel breaks, as well as natural features in the topography that they can rely on. And so you might think that might be questionable that we still have these pockets of deep green or low risk on such a high fire risk day. This has been corroborated by folks in South Florida that they really do consider these areas low risk because they are so much more likely in some cases to retain water throughout the year. In the center here, we have, again, our kind of quality prescribed fire day. So you can see the road, or kind of this linear boundary. You can actually see the road running east to west here. The fire that was lit from the road and then burned out into a lower risk area. So moving from that moderate risk where things are dry enough, but not too dry, and moving into a wetter, low risk area to put itself out. And then green, we're entirely green, which is what we want to see. You might see some of these specks in here of lighter colors. These are just places where the DEM is sort of anomalously high, and so it does funky things to our water levels, which is, I'll circle back around to DEM improvements here at the end. So we don't want to just cherry pick days where we think our model looks like it's doing well for visualizing perceived risk. We also want to make sure that it can capture general seasonality. So these are runs from January to July, 2017 to 2022. And these are all run on the 15th of each month. So we have kind of greener with a variety of moderate fire risk mixed in January, February, and March, heavy fire risk in April and May, much brighter things light up, and then a significant greening into June and July. So we want to see this arc of maybe quality conditions for prescribed fire, moving directly into wildfire season, and then coming out of that risk in June and July. And we're also able to capture years that maybe don't fit this pattern as well. So in 2019, they had a drier than normal winter. They ended up getting precipitation in February, which is not quite as usual. So higher fire risk, moving into lower fire risk. And then you can see that the wildfire risk never really quite picks up like it does in the other years in April and May. So we're able to capture these through the different water levels that are modeled by USGS. And finally, our if-then statements again, but now very quickly paying tribute to how energy release component can be used to modify the model outputs, as well as recent burn history to get to our eventual fire risk. So energy release component, or ERC, is simply a way to estimate fuel conditions, both live and dead fuels, and how they might contribute to fire intensity. It can change on a daily basis, but it's a little bit of a lagged index, so you don't expect dramatic changes day to day, but it takes into account daily moisture and temperature. And so we average that data from these 7 stations across the landscape, and it is also classified based on a historical data risk thresholding, 97th, 90th, 80th percentile. And so we've created essentially a crosswalk of how ERC may slightly elevate landscape risk based on its high or moderately high, or slightly decreased landscape risk if ERC is low. For fire history, we use the most recent 3 years of burn boundaries, so both prescribed fires and wildfires. We're not concerned if a burn happens twice in one location. Yes, we know that to affect the fuel loads on the ground and how a fire might behave. But we're simply just saying, yes, it burned, no, it didn't in this iteration of the model. And this is currently put in manually. We'd like to find a way to automate that into the future. But for now, we prorate or reduce our fire risk based on the fuel type that that fire footprint occurs in. So if it's in a grass or shrub dominated fuel type, we reduce risk only 1 year post burn. So full risk class reduction going from high to moderately high for 1 year. If it's in one of these four, so barren, urban, ag, open water, it's reduced 2 or 3 years post burn, mostly depending on the management unit. Most reductions are 2 years. And then finally, we have in our pines and our tree hammocks and our cypress domes, risk is reduced for up to 3 years, depending on the management unit. And so these are just 2 images on the right, our core output map on the left, 5-class risk. The center image is ERC adjusted, which this is very coarse. It's an approximation. It needs some improvement, but we have elevated overall landscape risk, taking what was low risk to moderately low risk as a general adjustment to how they might think about fire risk. And then the map on the right in these pink highlighted areas, pink highlighted squares. If we look back over to our first map on the left here, we can see that we go from yellow to now we're mostly dominated by moderately low. And so these aren't all the places where risk is reduced within the burn footprint, but these are just some of the more visible ones to look at. So with that, I realize I'm coming up on time. We can pause and do questions and then maybe go to the fourth section. But our future work for this is to continue and iterate on those risk breaks and risk threshold assignments for each management unit and fuel type. We also like to eventually be able to create outputs or overlay some more real-time forecast data, things that our managers are considering absolutely alongside the output maps if they're using those. And then finally, I've alluded to this a couple of times, without a legend here, we have differences between the first DEM and the second DEM. We'd really like to have a third data product to bring online and do a comparison and maybe do some smoothing or some averaging across the 3 products to get us closer to what is a real ground surface and maybe not bias too high or bias too low in any given location. And with that, I'll pause and check in with you, Elliot, and then I can jump into section 4, depending on what you think we have time for.
Yeah, great. Thank you, Kate. If anyone has any questions for Kate, you can throw them in the Q&A right now. I wanted to go and start off with just at least one question of mine. I have several, but I'll start with just one for now. I think what really stood out to me as you were telling me about this project is just the degree of collaboration and co-production that you were using. It was really necessary in this work. And that was obviously a critical piece for being able to have high resolution models that use really area specific data. But it also seems like it was a uniquely heavy workload to one workload on its own, getting all these new data products integrated. Another one maybe to actually use this co-production approach. I was wondering if you could share any more about that process and like any particular challenges, because if people wanted to apply the same approach to their specific area, they'll have to work directly with the managers like you all have, and any takeaways that can inform how they do that.
Yeah, absolutely. Yes, I think is the ultimate thing to say. It is extra time on the research and the geospatial development, but really extra time and thought and learning to speak the same language and create useful things, but needing fire manager input, right? Like none of this could have been developed without the time and the multiple Zoom conversations and the follow-up emails that I've sent to people to just kind of help me flush out what exactly we're talking about and understanding the system. And none of that really makes up for just going and visiting the place. So as someone who is from the mountains of Eastern Tennessee, thinking about a very flat landscape, grass dominated, just a totally different world for me, not a ton of reference point other than being a geographer and being curious about systems in general. I think this is a take home for maybe any project ever, but building those relationships and finding that person that, yes, you can email formally and have a schedule with, but you end up with some working rapport, and you learn to speak the same language about, when I say this, I mean this. And so many people in the National Park Service were willing to dedicate their time and join these meetings and provide feedback. But specifically, Jill Hausnecht and Justin Shedd, who's in the regional office, they were major, and still are major, facilitators of this work and proponents of this project, because there are many times where it could have stopped, or it could have stayed with some iteration of version 1, whereas now I feel like we have momentum, or hopefully some momentum, to really continue to refine it into the future in a way that it remains useful for them.
Great, thank you. We have had a few questions come in.
Okay.
I'll start with what I'm seeing first, which is a question about how recent precipitation is factored in. So expanding on it, saying, for example, if water levels are low over the long term, but short-term rain is increasing moisture levels in the fuels.
Yes, that's a great question. So you'll notice that we don't go into really too much of the details or the physics of how fire will burn and fuel moisture, et cetera. We in this model mostly rely on the water levels. The ERC is the only other metric that would truly be updated in a daily sense of giving idea of fuel moisture levels increasing or changing in the near term. I think there is a significant amount of room for improvement, and really the number of other side projects that spawned from working on this model and realizing some of the, in some ways, gross generalizations that we needed to make based on the scope of the project and what we had data for. Yeah, there's certainly room, and there should be other components of fuel moisture incorporated.
Great, and then another question that came in was asking, I think you touched on this a little bit, but what would it take to expand this model westward onto state land specifically? So say that, seems like you touched on it because you have these supporters in the Park Service and everything. That might be one thing, but what else do you think it would take to expand this to state land specifically?
I don't want to say anywhere there's a water surface you could find a way, but really the water surfaces, if that is a main consideration concern, if you're trying to truly replicate FireHydro in a new area, some gauge-based measurement. Now it's very nice because we can go out and automatically download, we pull down the Eden data automatically within the model. It's georegistered, has a projection, all sorts of different things. If somebody had a gauge network in a location, you could start to build something like that, a standardized water level surface that could be produced as often as the gauges were taking measurements. But that's certainly not a small feat. So we're in some ways currently constrained by where the Eden water surface exists.
Okay, and then another one, someone's asking about the choice to average the 7 ERC measurements together instead of picking one in the projected area of concern. So they're saying that even on their national forest, their ERC per station can differ by 7 to 8 points. Yes, that's a great point. They do differ from those different stations across the landscape. From my understanding, most of the decision to average was one, because we were encouraged to do that for just our original model outputs. There has been some conversation about Big Cypress and Everglades using different ERC thresholds for risk. So the stations would then be subsetted out into the 2 parks, but there has not been any mention of using a single station for a localized area. I think mostly because I dare say there aren't that many stations for the entire landscape. I know you're not going to have raw stations in very, very close together for a true model interpolation, but you could create some spatial surface or modeled surface from the ERC measurements in a really simple interpolation. That is possible. Okay, I think we have time for one more here. The final question is asking about the challenges to using this model regarding phenomena like El Nino or La Nina or climate change in general. Kind of asking how well should this be able to work well into the future as we have those long-term changes? That's a great question. So we're not considering
truly, as an input to this model, any type of climate or oscillation occurring on, multi-year or multi-decadal. We're really relying on essentially deterministic data products collected from the now. We are using the historical water level distributions, which on one of my intro slides, I alluded to the fact that flow is changing, that may or may not be directly linked to climate change and how they choose to manage into the future. One way that I would see the model responding to more anomalous, drier or wetter years into the future is making sure that you're always shifting the window that you're collecting historical water levels from, because certainly if you're looking at historical water levels that are now no longer indicative of the present, that distribution has changed enough it's no longer meaningful, then yeah, you're sort of kind of not quite garbage in, garbage out, but you need to make sure it's updated.
Great. Okay. Well, there were a few more questions here. I'm sorry to everyone that we didn't get to your question. I posted Kate's contact info on the screen here. So if you want to follow up with her directly, then you can reach out to her by her email address there. Just want to thank everyone so much for attending, and thank you, Kate. Really enjoyed the presentation. It's really good work showing how to really cater to specific regional needs and how to do that. So thank you again, and we look forward to seeing you all on the next one.
Thank you all.